Alright, so the most complicated topic, the one that won the vote of sorts for the reflections, was the chymotrypsin mechanism. And so I'm just going to go through that again. I can't really promise that I'm going to explain it any differently than I did before, because really that's the only way to explain the chymotrypsin mechanism, but I will do my best to make it a little bit more clear and a little bit more comprehensive. So what I'm going to put up here is kind of the stages one by one, and we can talk about them a bit. This is the first stage. So a number of things are going on here. First, we have histidine 57 in the active site. That's going to act as a base and an acid, respectively. It's going to accept protons, donate protons, accept protons, and donate protons. We've got serine 195. It has a hydroxyl group on it, and that hydroxyl group is going to act as an attacking nucleophile. That's the hydroxyl group right here. So we'll be coming back to that in a second. And we have a hydrophobic pocket. A number of you said that it was the hydrophobic pocket that you really didn't understand. What we mean is that lining this face of the protein right here are many, many hydrophobic residues, hydrophobic side chains. And so the protein that's going to be cut by chymotrypsin, the substrate that's going to be cut, has a hydrophobic side chain there as well. So the hydrophobic side chain R1 fits and nestles very nicely in the hydrophobic pocket, and that lines the substrate up in this configuration. So the reason why the peptide bond is right here, the reason why the peptide bond is correctly oriented in three-dimensional space to be cut by this enzyme is because the substrate is situated in just such a way so that that peptide bond is lined up for cleavage. Part of what's situating the substrate in that way is the binding of this side chain into this hydrophobic pocket. So that's what we start with. So a number of things are going to happen in step one, and I'm going to describe what's going to happen by looking at one figure, and then we can go ahead and see that occur when we look at the next stage in this mechanism. So the first thing that's going to happen is that this proton is going to be donated to this nitrogen of histidine. So histidine is acting as a base in this case. And that's going to make this oxygen a free radical. It's going to make this oxygen very antsy and very reactive. This oxygen with that unpaired electron is going to attack the carbonyl carbon right here and make a bond with it. So let's go ahead and see what happens in that case. So now that bond has been made. It's this bond right here. We're in the next step of the mechanism. We see that the proton has been donated to histidine. So histidine has been acting as a base in that case, and the proton has been donated. And because of this bond that we just created between the oxygen of serine and the carbonyl carbon of the substrate, this carbon has to always have only 4 bonds made to it. So in order to make that bond with the serine oxygen, this bond right here was converted from a double bond to a single bond. If we go to the other mechanism, we can see that that bond with that oxygen was a double bond before, giving carbon 1, 2, 3, 4 bonds. Now, in order to give carbon 1, 2, 3, 4 bonds, we had to lose that double bonded oxygen bond. That makes this oxygen very reactive. It's negatively charged now. It has an unpaired electron, and so it is not happy. So this is our transition state. This is an intermediate of the substrate halfway through the reaction. We've bound the substrate to the enzyme directly through the hydroxyl oxygen of serine, and that binding has created a reactive group on the substrate itself. So I'm going to clear this off of the screen now and move on to step 3. I'm going to reload the picture, so bear with me for just a moment or two. So what happens between step 2 and step 3? Well, what's going to happen is that that reactive oxygen, with its unpaired electron right here, is going to attack the carbonyl carbon. It's going to launch another nucleophilic attack, and it's going to essentially demand that that carbon make another bond with it, a second bond, restoring the double bond that we had initially. In order to make that 4th bond with oxygen so that that carbon has 1, 2, 3, 4 bonds, the peptide bond itself will have to be severed or cleaved. If we go over to step 3, we see that's exactly what happened. Here is the double bond with that attacking oxygen. That's the same oxygen that just launched the nucleophilic attack. That's leaving carbon with 1, 2, 3, 4 bonds. Because those 4 bonds were made, including the double bond with that oxygen, we severed the peptide bond. When we severed that peptide bond, nitrogen, which always wants to have 1, 2, 3 bonds, was left a bond short. In order to be satisfied, nitrogen needs to make 3 bonds. So what nitrogen did to restore its 3 bonds is it stole this proton that histidine had been holding. In this case, the nitrogen is acting as a base, and histidine is acting as an acid because it donated a proton. So the reason why this nitrogen has 2 hydrogens that you see here is because that second hydrogen came from histidine. There is nothing holding this half of the substrate to the enzyme any longer, and it floats away as the leaving group. Essentially, we've cut this peptide bond, and the enzyme has done its job, but enzymes must recycle. And if we started off with an enzyme that really had nothing in the active site but substrate, so essentially, if we go back to that first diagram, this is the guts of the enzyme, and we can see that what we're left after step 3 is with something completely different. And so we have to fix that. So the rest of the mechanism is for restoring the enzyme back to its original configuration. In step 4 of the mechanism, in floats water. This is polar water with partial charges, and the hydrogen of that water can make a hydrogen bond with the nitrogen of histidine. And that's what we see there in the dotted line. Once that hydrogen bond is made and those electrons are being pulled from that hydrogen, that creates a lack of ease in this oxygen. And this oxygen is then going to do what the oxygen of serine did in step 1. It's going to launch a nucleophilic attack on that same carbonyl carbon. That's the same carbon we've been attacking the whole mechanism here. When that oxygen launches that attack, what's going to result is that we are going to make a covalent bond with that oxygen and carbon. But carbon can only have 4 bonds at any one time. 1, 2, 3. And so we are going to have to remove one of the 2 bonds that carbon is making with that double bonded oxygen right now. If we go to step 4, we'll see that's exactly what happened. Water, the oxygen of water, has made a covalent bond with that carbonyl carbon. That carbonyl carbon remains at this point bound to serine, and the only way that we can have those 4 bonds with that carbonyl carbon is if we reduce that double bond to that last oxygen to 1. This oxygen is now very reactive, it's negatively charged, it has an unpaired electron, and so it does what it did just a moment ago in step 2. It launches its own attack on that carbonyl carbon. And that carbonyl carbon is going to have to give that oxygen a second bond, a double bond. If it remained the way it is now, that carbon would have 5 bonds, and that's not okay. So the bond we're going to break this time to satisfy that attack is this bond right here. We're going to sever the interaction between serine and the carbonyl carbon. If we go on to step 6, we'll see that's exactly what happened. There is no longer any bond between the oxygen of serine and the carbonyl carbon. Instead, we see that there is a double bond satisfying the oxygen, a single bond still with the side chain, and a single bond to the oxygen that it had been interacting with before. That's the oxygen from water. So this oxygen, I'll highlight it in green. This is the oxygen from water. That is the same oxygen that this carbon is now bound to here. In order to launch that attack, in step 5, the proton that was engaged in a hydrogen bond with nitrogen when water entered, that proton was accepted fully by the nitrogen on histidine 57. In that case, histidine is acting as a base. It's accepting a proton. That accepting of that proton allowed this oxygen to launch that attack. But when we started the mechanism initially, histidine was not protonated. If we look at step 1, the proton is on serine. It is not on histidine. And so the last step to recycle this is that histidine donates its proton back to serine, the oxygen of serine that just lost its bond with the carbonyl carbon. And so now we have a recycled enzyme where that proton is now bound to serine, the hydroxyl group in serine is restored, the proton was donated by histidine 57, And so histidine 57 once again acted as an acid. And now we've recycled the enzyme back to completely what it was before. There's one small exception. It's important to keep in mind that this proton, this is the proton that came from water in step 4. This is this proton that was transferred first to histidine and then transferred back to serine. But if we compare our step 1 of the mechanism, and we see that serine contains a restored hydroxyl group, histidine does not have a proton. If we come back to the end of step 6, we see that serine has a restored hydroxyl group and histidine is not protonated. So we've recycled the enzyme back to what it was when we started. What the schematic doesn't show is that the other half of the substrate will now act as a second leaving group. It will leave the active site, and the active site will be empty, the hydrophobic pocket will be empty, and we're ready to accept the next substrate and do it again. So if we take the mechanism in total, we kind of clear off all the drawing. If we summarize it, we see that in step 1, substrate enters and is lined up. The oxygen of serine attacks the carbonyl carbon, and the proton is transferred to histidine. In step 2, we have our transition state. A reactive carbon on the substrate itself attacks the carbonyl carbon for a second double bond, and that causes the peptide bond to be severed. In step 3, half of the substrate leaves as a leaving group. In step 4, oxygen enters the active site. It couldn't enter before because there wasn't room for it. Not oxygen, I'm sorry, water. Water enters the active site. It couldn't enter before, but now it can. And as water enters the active site, the oxygen of water is going to launch an attack on the carbonyl carbon. At the same time, that water molecule is going to donate a proton to histidine. In step 5, half of water has been bound covalently to the second half of the substrate, and histidine has accepted the proton from water. That leaves a very reactive carbonyl oxygen on that substrate molecule. And we see in step 6 that oxygen launched its own attack on the carbonyl carbon, forcing a double bond to be formed. That double bond formation causes a break in the bond that was holding the substrate to serine. Serine is now recycled to a hydroxyl group by accepting the proton that was being held by histidine, and that second half of the substrate is free to leave the active site itself. The other thing that's important to note is that the transition from step 1 to step 2 has histidine acting as a base, accepting a proton. The transition from step 2 to step 3 has histidine acting as an acid, donating a proton. The transition from step 4 to step 5 has histidine acting as a base, accepting a proton. And the transition from step 5 to step 6 has histidine acting as an acid, donating a proton. This is why this is a perfect example of the chymotrypsin mechanism of general acid-base catalysis, because we see histidine acting as an acid and a base twice throughout the enzymatic mechanism. I know that's pretty much how I explained it in class, but there's really only one way to go through the chemistry of this mechanism step by step. I'm hoping that by recording it and kind of showing the mechanism all in one shot, having the whole mechanism up there at the same time, you can rewatch this and see those electrons be pushed and kind of track the transfer of this reaction from substrate to product as we go through it step by step. I really hope it helps.